Right, components of an atom and radiation. I can't believe any of you don't know this stuff already. Is anybody at all confused about that issue? Good. Isotopes. Anybody have any problem with definitions of isotopes and what isotopes mean? Excellent. Did you know that it was in fact a Scottish doctor, lady doctor, who came up with the term isotope, coined in 1913 by Margaret Todd, during a conversation with Frederick Soddy, and Soddy was the guy who really did the early work. Natural decay processes. So we are not talking about fission or fusion. We are talking here about natural decay processes. Again, have you all done this in physics before? Yeah? Has it been a long time and you need reminding? Okay, good. So alpha, beta, gamma are really essentially the three things. And has anybody found this on Moodle yet? Has everybody looked for the notes yet and found them on Moodle?
Just the name. Yeah,
Oh.
it is there.
It is good. Good. Okay.
Yeah.
Alpha decay occurs when the atomic nucleus ejects an alpha particle and transforms into nucleus. So there we go. We also write it like this. If the alpha particle attracts 2 electrons, it becomes a helium atom. Sounds trivial? It's a big deal in nuclear. That is a big deal. The issue of alpha decay giving rise to helium is a big deal. Typical kinetic energies of alpha particles are about 5 MeV. They vary, you'll see in a minute. Beta decay, we call it beta, it's not, it's actually beta minus. Occurs when a neutron is converted into a proton plus an electron and an antineutrino. There you go, that's actually what we're talking about. And if it produces a positron, then it's beta decay, it's an electron, it's beta minus, strictly. Frankly, I call it beta. It's fine. The electron has an energy of roughly half of MeV. You then get, for example, here's the strontium goes to yttrium, plus a beta particle, then the yttrium undergoes beta decay to zirconium 90, emitting an electron with 2.3 MeV. So depending on the reaction, and you're going to see why in a few moments, the energies of the beta particles tend to be quite different. About 5% of the energy, roughly, is the antineutrino. How much effect does the antineutrino have on the material's performance or whatever? Absolutely none whatsoever. In fact, while you've been sitting here, you have been irradiated thoroughly with neutrinos. Neutrinos are washing through this room as we speak. Where have they been produced? In the sun. They are such weakly interacting particles. We are sitting here in a sort of stream of neutrinos which just go straight through the Earth. I think the probability of the Earth capturing a neutrino or interacting with a neutrino or scattering a neutrino is kind of 0.5% or 1% of any neutrino that crosses the Earth. So it's really, maybe that may be wrong by a factor of 100 or something. It's really small, very small indeed. So they're totally negligible in that regard. Gamma are emissions of high energy electromagnetic radiation. Gamma rays are often produced alongside other forms of radiation, as we will see. When a nucleus emits an alpha or beta particle, the daughter nucleus is sometimes left in an excited state, and it will then jump down and produce a gamma ray. And they are typically of the order of 1 MeV. So you know about electrons, and you know how electrons sit in energy levels around an atom. Well, it's exactly the same for nucleons in a nucleus. They sit in energy levels. The only thing is they usually all sit down at the ground state. But after a decay, some of them are left in an excited energy state, and then they drop down from the excited energy state to a ground state, and they give out a gamma ray. What happens if you've got an ejected electron from a core orbital of an atom, and it goes up, and then it drops back down to the low energy level? What does it give out? Energy in the form of a... No. So an electron falls down to an inner shell. So it's a big, big transition, a lot of energy. What does it give out? Aha! It's the penny dropped. It's called an X-ray. Okay? So electron transitions give rise to X-rays. Nuclear transition gives rise to gamma rays. Just out of interest, does anyone know the difference in terms of the electromagnetic spectrum between a hard X-ray and a gamma ray? I said a hard X-ray and a gamma ray.
Basically, that's the only difference. And the X-rays usually go for larger rates and get the wave of faster than the gamma rays.
Yeah, but we're talking about kind of, you're absolutely dead right. In other words, really no difference. It's just the way we talk about it. If it's a nuclear transition, we talk about gamma rays. If it's an electronic transition, big one, we talk about X-rays. But actually, of course, it's exactly the same thing. All it is electromagnetic radiation. It just helps us keep track of which bits of the spectrum are coming from what process. That's all. Natural decay process. If any of you can't solve that equation, you should be taken out and severely beaten. I'm sure you've seen that before. So what do? Integrate both sides, exponential to solve, trial function to solve the integral, and you end up with this term here. So the lambda is the key, it's the decay constant. Lambda is the decay constant. And the lifetime of the radionuclide Tor is the reciprocal of lambda, and log 2 over lambda is the half-life. That's it. So again, I can't believe you've not all done this before, but it may have been a few years ago. I certainly expect you to be able to, in terms of exams and things, to be able to sort of remember how to do those sorts of things. And there'll be some little questions in the text later on. So this brings me on to the history lesson. And so far we've thought about something called spontaneous decay. Spontaneous decay proceeds in terms of statistical laws. So the exponential decay is a statistical law. Here is an atom, and it's going to undergo alpha decay. When will it, if it's got a half-life of 8.03 days, will it have decayed after 8.03 days? Exactly. Who knows? This may stay there for 1,000 years, and it may decay. It could go in the next 3 nanoseconds. That's the whole point. It is simply a very unsatisfying statistical process. If I've got a block of iodine-131, which has a half-life of 8.03 days, then how much of it will be left after 8.03 days? A half of it, on average. It's a statistical process. 1919, Rutherford, who, as you all know, is a Kiwi. How many of you knew that Rutherford was a Kiwi? There you go, you see. I'm not sure whether I should say that here. Anyway. Discovered that nuclei can be transmutated by bombarding with alpha particles. So this is what, when people talk about splitting the atom, this is the thing. He split the atom. And the first example was with nitrogen. So nitrogen 14 plus an alpha particle produced oxygen 17 plus a proton. And he got the Nobel Prize for this. Do you know the famous story about Rutherford? He said he was a physicist's physicist, full-on proper physicist. And he said that there are only 2 sorts of science, physics and stamp collecting. He got the Nobel Prize for chemistry. Didn't turn it down. So, anyway, soon afterwards, lots of other examples of this sort of stuff. And the famous one, of course, is Irene and Frederick Joliot-Curie, who discovered artificial radioactivity. So there she is. It's her husband, and she is Madame Curie's daughter. So it's really did follow through. They've got the great French science dynasties, even though Marie Curie was actually Polish. But anyway, Nobel Prize for Chemistry in 1935. And what they did is they irradiated aluminium with alpha particles to generate neutrons. So aluminium 27 plus helium goes to phosphorus 30 plus a neutron. And what they found is that the radiation continued to be emitted after the irradiation had stopped. So what Rutherford did is he sort of banged away at this stuff and it gave out this other form of radiation. Wow, he split the atom and he did this. But he turned this experiment off and it all stopped. What they were able to do is that they created this artificially radioactive material which continued to decay via beta plus particles, i.e. positrons, so positive electrons, afterwards. So they produced artificial radioactivity, and that was the first time in 1934. The speed over which things developed in this area over this time period is absolutely astounding. So after they discovered artificial radioactivity, it was hoped that you could bombard heavier elements such as thorium and uranium, and you could get to even heavier transuranic elements. And indeed, you can, and we do this. In nuclear reactors, this process happens all the time. Uranium is bombarded with neutrons, and you can produce plutonium, for example. So, very important process. But in 1939, Hahn, Strassmann, Freisch, and Meitner discovered that neutron irradiation of uranium, which they were going to try and build these heavier elements, like in a star, but what they actually caused was fission. So they did a bit of this, but they actually found that the uranium, they were able to detect barium and krypton. They detected the barium chemically, in fact, is the way they did it. And so they actually split the uranium into two fission products. And indeed, there was a Nobel Prize involved. Although Lisa Meitner did not get the Nobel Prize. And you can read all about that and the controversy and you know, you have to remember this was in 1939, and so you can imagine. But it's a very interesting story indeed. 1942, scientists at the Metallurgical Laboratory isolated first wave amounts of plutonium. That went then to Oak Ridge, a Y division in Oak Ridge, which is still there. And they took this plutonium and they put it into a graphite moderated reactor in here. There are paintings of this. I've always wondered why there are only paintings of these things, not photographs. I don't know, but I have a feeling it's because any photographic plates that were taken in fogged up quite quickly because they didn't understand about shielding against some of these processes. But anyway, that is not in fact a smoke cloud, that is a tree growing out of an old stadium, and underneath this old stadium, which was falling to bits, they created this graphite pile. So a pile is a sustained nuclear chain reaction that isn't being used to generate electricity. You aren't collecting the heat, you are venting the heat. If you vent the heat, you're not using the heat in any way, it's called a pile. If you use the heat, it's called a reactor. I don't know why, it just is. So, 2nd of December 1942, under the abandoned West Stand Stag Field, Chicago Pile 1, CP1, and the Italian physicist Enrico Fermi's pile produced the first self-sustaining nuclear reaction. Here it is, they're looking on, there's the pile, and you can see there's a guy just down in here, okay, and who's got the fine control process stood in the bottom there. What you can't see very well is, so they have a series of cables going up which would drop in the neutron absorbing materials if the chain reaction took off too much. And he's down there and he's got an axe. And if it all goes horribly wrong, his job is to cut the cables and drop the things fast into the reaction and stop it going what we call prompt critical. And prompt critical is something you're going to learn about from Dr. Wenman next week. So he was the safety cable release Axeman. Right? He was the safety cable release Axeman. And that's why we talk about scramming a reactor. When you shut the reactor down very, very quickly, you scram the reactor. That's why. And there he is. At least that's the story I've been told. I don't know, maybe it's not true, but it's a great story. And then, 3 years after that, you have Trinity, Manhattan, and by the way, you can go, and indeed, this is a particular photograph, and you can stand right next to that. And on the ground, there are pieces of molten desert, where the heat from that explosion melted the glass and produced a material called trinitite. And you're not supposed to pick any of it up and take it away with you. It is actually, if you were to do something like that, which I couldn't possibly condone, and you put it next to a counter, you get almost no counts off it at all. And it's a beautiful sort of green colour as well. But as I say, I wouldn't condone going there and taking any of that material. They will shout at you if they spot you doing it. If they spot you doing it. And you know the famous thing about Oppenheimer and so forth. By 1951, I mean, the rate is incredible, actually. By 51, they had the first reactor to produce electricity. And it produced enough electricity to light 4 200-watt light bulbs. There it is. And it was called the Experimental Breeder Reactor number 1, or EBR1. And there it is. That is the actual reactor building. If you go inside now, there's nothing there. It's all gone. It's completely taken away as nuclear waste. Utterly. That's got nothing to do with the reactors. Those are reactors. Those are test reactors. We're trying to make reactors small enough to power aeroplanes. And they were not very successful. But there you go. That is exactly where it is. And if you ever go to this place, it really is utterly in the middle of nowhere. And then you go a long way further. It is unbelievably remote. It really is. And they really weren't sure. What's really fascinating about this reactor, it was a fast neutron spectrum, combination of natural and highly enriched uranium metal furans, and the sodium-potassium eutectic coolant. I don't know if you take sodium and potassium, the metals, of course they're both solids at room temperature. If you mix them up, they actually melt. The eutectic, do you know about eutectics in material science? So essentially, this is the melting point, this is temperature, this is composition. So if that's pure sodium, that's pure potassium, then actually, sorry, that should touch there. That's liquid, that's solid, that's liquid plus solid, that's liquid plus solid. But the point here is that you have this massive depreciation of the melting point of the solid here, somewhere between the two end compositions. So that's a solid at room temperature. So if this is room temperature, pure sodium's a solid, pure potassium's a solid, but the mixture's a liquid. Classic material science. So they used sodium potassium eutectic coolant. You can imagine how reactive that is. They had a fast neutron spectrum, which is incredibly difficult to control, particularly in those days, and they were breeding plutonium in the reactor, as well as producing electricity, because in those days, of course, the power programs and the weapons programs were intimately mixed up, and they were desperate to produce more plutonium. And this was one of the ways that they went about doing that. Very, very quickly after that was 51. 2 years later, we have the Eisenhower Atoms for Peace speech, which is really worth listening to, and the establishment of the International Atomic Energy Agency, and the beginnings of nations like the UK and the US splitting out their power and weapons programs. It actually took a very, very long time for that to happen, and certainly in the UK we didn't have that process completed till the mid-60s. But by that point, the production of weapons-grade materials, and we'll talk about the difference between weapons-grade and reactor-grade materials later on, because it's very important. The process really started here with this speech, so it's well worth reading. And then by 1954, I mean, you just go through these just very quickly. 34, first time anything like this was ever discovered. You know, we're talking Nobel Prize territory. 10 years later, they had a reactor and a bomb. 10 years after that, they had the first nuclear reactors putting power into the grid. 20 years from basically discovering stuff to actually plugging a reactor into the grid. It's absolutely astounding. It's so quick.
There was a war.
That's a very good point. There was a war. Yeah. And then there was a Cold War. And the Cold War was actually just as important as the war. No, I know, it's sad, isn't it? But there you have it. So, 1954, world's first nuclear power plant to generate electricity to power a grid was started in the USSR, not in the UK, not in the USA, but the USSR, as it was, back to the USSR. And it had 5 megawatts, so it's not very big. World's first commercial nuclear plant, we would argue, was Calder Hall in 1956, and that had, well, originally 50 megawatts and later 200 megawatts. And then the first reactor, the Americans would argue, to produce electricity and then undergo a complete decommissioning back to greenfield sites was the Shippingport reactor, which was a light water breeder reactor, interestingly. And that was in 1957, operated for 25 years, decommissioned, down, done, land released. It's in barrels in the Tri-Cities area now. Okay. Oops. Do you want to keep your ink? Thank you. Don't save. I'm not sure I made any changes, so let's not save them. Right. Have I used up all my time? So that says 8 o'clock and it's not, it's 7. Sorry? 9 o'clock? Bloody hell. Struth.
You're only getting that. You're just getting a bit in the UK. Yes, that's you're the next one.
Holy moly. Okay. It's going to be a long week. Isn't it? I didn't know these lectures were at night when I signed up for this. I just want you to be, I want to be quite clear about it. Right, okay, so this is lecture 2. So we're not going to get through the whole of lecture 2 today, at all, not even close. But that's okay, because I have something like 6 or 7 of these kind of lectures. So going at this sort of, I mean, again, I've not done this before with this audience in quite this way with this course. So is this rate of travel about right for you? It's okay? Would you like me to be going faster? You've got that kind of wanting to go faster look about you? No? You sure? This is okay? All right. I mean, just let me know. Okay, so radiation fundamentals. So what we're going to start to do now is think about the way that, where are the engineering challenges in all of this? You know, you kind of see where everything's come from. We're at the beginning now of an age where we're going to build nuclear reactors. The first 3 reactors are being powered to the grid, and we've got to start to make some choices as to what kind of reactor designs are going to power us through the latter half of the 20th century, and see what happens. So what were these people thinking? Well, they were starting the process of looking at radiation damage and radiation effects. We're going to do a lot more of that tomorrow. But they were also starting to think about how they protected themselves against the effects of radiation. So in other words, things like shielding. Fermi was in the process of dying at this point because of the effects of radiation. Madame Curie died basically because of the effects of radiation. So people were starting to understand that this was a serious business.
Don't have fingers rotted off or something?
I don't know, actually. I don't know.
Something about their fingers missing because
I think certainly that he had leukemia, but he was Pierre Curie was
being hit by a carriage.
yeah, he was hit by a carriage, but he had leukemia by that stage.
Yeah.
Her notes are still contaminated. Oh yeah, there would be. I mean, radium's got a really long half-life. Yeah. Well, I worked at a place called the Royal Institution in London, and these people had given lectures, and there are famous paintings and things of when Röntgen came and gave a lecture on X-ray, and he had his X-ray generator, and he had a zinc oxide fluorescent screen, and there's actually there's a screen just here so that you could see it. There's the X-ray generator here,
Yeah.
and they got a little girl from the audience to come and stand in between and move so you could see her bones as she moved. I mean, when I was a child, if you went into a shoe shop, in certain shoe shops, you could put your foot into this machine, right, and you could see your foot inside the shoe, so you could see whether or not the shoe was fitting around your, you know, it was kind of a. It was just a gimmick, right? It was a gimmick, but that was an X-ray generator they had sitting there. I mean, if you want to see some. If you want to see some real panic in an airport who ask you to, you know, those machines where you stand there and they do the very soft look to see whether you've got anything, you ask them about the dose you're going to get. Now, actually, the dose is trivial. It really is trivial. It ain't going to do you any harm at all. But they get very nervous if they think you know anything about radiation. They really do. But no, these machines, you put your foot in, you know, you really were getting quite a solid dose by doing that. And that was in the 1960s. So we have come an awful long way in our understanding. And now, of course, we've gone, as you say, to the other extreme. But nevertheless...
They had this machine where there was removed facial hair for women. So you place into like an X-ray machine, they put the X-rays on the face and sort of the hair would fall out. And then months later, their faces started to rot. So they made quite a lot of money out of it with these two, this father and son. But then once it got out, it was causing damage. They eliminated the machine.
Well, you know, think of early tanning machines, I mean. Crackers, isn't it? Still, never mind, there we go. We live and we learn and we move forward. And actually, so my father was a physicist, and he would never let us go anywhere near the machines to put your feet in. Because he knew, you know, why do you want to do that? So in the 1960s, or 70s I guess, he knew that this was not a good idea. So you know, you can make a considered opinion based on your scientific knowledge as to what will keep you safe and what will not keep you safe. High energy photons, X-rays and gamma rays, energy is transferred to form an energetic electron and forms an electron-hole pair. Electrons, beta particles, Coulomb interactions called inelastic scattering. So first one, right, you form electron-hole pairs as the gamma ray goes through. We're going to go into this in more detail in a few minutes. Electrons, they're charged, they cause inelastic interactions. So inelastic means that basically it's electronic excitations. So what's an elastic interaction? How many of you play snooker? Or would you say snooker or billiards? Pool. Wow, no, because you hear a click.
Yeah.
Yes, roughly. Okay. So, inelastic interactions and ionisation, but also Bremsstrahlung radiation. So Bremsstrahlung, who speaks German? So nobody speaks German? Not even a little bit? Sorry? Well, yeah, so would I. I mean, I shouldn't say it like that. I'm very useless at this. Braking radiation, absolutely. So what happens is that the electron is forced into a curve, or is forced around, and because it's being braked, it's producing electromagnetic radiation, so that's Bremsstrahlung. So, if you want to protect yourself against beta radiation, if you're going to end up in a situation where you really bend the electrons and then you shoot out a whole load of gamma rays, actually you can make the situation worse for yourself. So shielding is not just a question of stopping, it's stopping in the right way. It's really important. Alpha particles, helium nucleus, charge of +2, bigger Coulomb charge, bigger Coulomb effects. Strong interactions due to high charge cause electron excitation, ionisation, but it also deposits helium into the material, and you'll see that effect later. We also do a lot of experiments with heavy ions, fission fragments, and primary knock-on atoms. We'll come back to that in a little while. Lighter atoms lose energy to electrons, heavier through elastic and inelastic collisions. Neutrons, again, we'll talk more later. Weak interaction. Can I move this out of the way a bit? Good. Neutrons, weak interactions because they're not charged. Elastic collisions that cause displacements, damage. Inelastic, causing excitation, nucleus or capture. Again, we'll write those out in a bit. And then protons, mesons, positrons, lots of research particles. They all have their own characteristics, so you can investigate different things by looking at the interaction of materials with these radiation types. These different radiation types. Why is that not going any forward?
It was over an hour before.
How about that? So, alpha, charged ionizing. As they pass atoms, they strip off electrons, causing formation of electron hole pairs, and they lose energy roughly equal to the ionization energy of the atom that you lose the electron from. So you have this trail. So essentially, the big alpha particle is heavy. It's got all the, and as it zooms through with that 2.3 MeV, it leaves this trail of electron hole pairs. It produces an efficient track. Some materials you can actually look at these fission tracks and you can see the residual damage, particularly in things like polymers, where it causes permanent bond breaking through ionization. In metals, it doesn't have very much of an effect because the electrons and holes combine so quickly because it's conducting material. Very different effects on very different sorts of materials. The neutrons, there are elastic scattering, so you're back to your pool, and then you have inelastic scattering. Radiative capture, so an atom captures a neutron, ends up in an excited state, gives out a gamma ray. You can have capture with a particle emission, N alpha and N proton. So again, captures a neutron, becomes an unstable nucleus, instead of, and it can give out, it can then do alpha decay, or it can give rise to beta decay. So you start with a stable nucleus, you add a neutron, it becomes an unstable nucleus, and it has a half-life because it's a different mass. And then finally, it can cause fission. So neutrons, actually often, the worst problem about neutrons is not the neutron irradiation, it's the other radiation the neutrons give rise to. That could be more damaging than the neutron irradiation itself. Let's have a look at some of these examples. So alpha and beta decay. So an example, we're going to compare alpha and beta. And these are really two of the most important. The cesium-137. So cesium-137 is a really important species. Why is it such an important species? Actually, I'll tell you in a few slides' time. Let's see if anybody knows why. Why is cesium-137 important? Why does it get us worried?
It ends up in grass.
It does, but why is it important?
You can produce several types of reaction.
Yeah. So cesium-137 decays to beta, to barium, right? And it's giving out a beta particle, beta decay, and a 0.66 MeV gamma. So it gives rise to beta radiation, and it gives rise to gamma radiation. The other thing is you produce quite a lot of cesium-137 in a nuclear reactor, and the half-life is 30.2 years. and we'll come back to this, but actually I'm going to say it anyway because it's such an important point. So if you've got a fission product in a nuclear reactor and you've got a nuclear accident, and if the half-life of the fission product is, say, 2.6 million years, which some of them are, is that likely to cause a problem? Half-life is 2.6 million years. Why? Sorry? Oh, the energy can be very high from the decay. Ah, yes. Yes, absolutely. What about then if you have something that has a half-life of a few seconds and you have a nuclear accident? Is that likely to cause? Because that's going to really have a lot of power associated with it. Dose, in fact, is what we would say. Well, by the time it gets to you, if you're stood away from the reactor, it's decayed. So it never actually interacts with you because it's all gone. The ones that are a real pain for us are the ones that last a few decades or a few days. So cesium-137, iodine-131, things like that, they're the really dangerous ones. Also ones that are taken up into the body readily.
Why not the ones that last actually continues to decay?
Because they decay so slowly. So the rate of decay, so that they're not giving out much radiation. Just, yeah, we'll write some equations down in a bit, but it's just not, you know, the number of atoms decaying is so few that the total amount of radiation given off is not very much. Of course, it will continue to do that for a million years. Whereas if it had a half-life of a few seconds, by the time I get it over to you, it's all gone. It's all decayed away. It's these intermediate ones that are the problems. And here's an alpha decay. So radium goes to radon plus an alpha particle here, and again you've got 0.2 MeV gamma, and you've got these two alphas. Most of it goes straight down to the ground state in terms of radium flow. Whereas, yeah, it's mostly, in cesium, it's mostly to the excited state. So in both these cases, two paths can occur with different probability, with one path leaving the decay product in an excited state so that a gamma is also emitted. For some decays, two or more excited states can occur, and in some cases, no excited states can occur. So they're all quite different. And you can see that there's a very specific energy here given out. So if I was to look at the spectrum of this thing, the spectrum would look like something like that. So you have these really sharp peaks associated with the gammas or with the alpha particles, if you were to try and do some sort of spectrum thing on it. On the other hand, with a beta decay spectrum, so that would be an alpha, for a beta decay spectrum, you tend to get a distribution looking something like that, although actually, again, if you've got more than one path, that would be for a single path, if you've got more than one path, you might have the thing looking like, but have on top of that so you could have something looking like that because you've got two. And indeed, if you've got a particular gamma that it gives off as well, you might even have something like that with a spectrum looking like this. And I've just made those up. I mean, you get all sorts of different things. So why do you get that? Well, remember that you get three particles with beta decay. It's that damned antineutrino again. Beta particle is so light, the nuclear recoil energy is practically zero, the decay energy is therefore shared between the beta particle and the antineutrino, which is almost undetectable. The beta particle energy therefore ranges from almost zero right up to almost the total of the decay. So the transitions occur to excited states, especially consist of several components, as I've just done. Antineutrino, which you can't detect, can still take quite a lot of energy with it, or not. Okay, we did the natural decay process already. All right, so isotopes of significance. So we're concerned with the release of different isotopes at different times depending on the circumstances. So now let's take what we just learned and look at the situation for Fukushima. And you've got iodine-131, which has a half-life of 8.04 days, and that gave rise to the most dose in the weeks, days immediately afterwards. What we were looking at, what we were constantly looking for the data from the Japanese on, was the amount of iodine-131 being given out. That was absolutely crucial. But after a month, we didn't care about the iodine anymore because it had all decayed away. You don't need many half-lives before it just doesn't matter anymore. And so a month is how many half-lives? 4 or 5. You know. So 2 to the 4 or 5. You know, 1 over 2 to the 4 or 5. So all gone. But cesium-137, half-life of 30.2 years, still hangs around. So those were the two for Fukushima. Chernobyl, because of the way that the reactor blew up, you had a series of other problems as well. And particularly the ruthenium-106 and 103 were particularly problematic. They produced a lot of ruthenium, and this was given off in terms of an aerosol particles, RuO2 and RuO3 aerosol particles. And they caused a lot of problems. Although the material, the isotopes you usually detect, first of all, by the way, are the xenon-133, krypton-85. There is a whole series of detectors around the world which just look for xenon-133 and krypton-85. Every country has a series, no, that's not true, not every country. The vast majority of countries have detectors in them looking for those isotopes. Why?
In their own backyard.
Gosh, I can't remember the acronym. CTBTO. Basically, we're looking for people doing clandestine nuclear tests. Clandestine nuclear tests, the telltale sign is the xenon. That's the one everybody looks for. It has exactly the right half-life, so you can detect it long enough after. Even if you do it underground, the damn xenon creeps its way through the fissures and pores in the rocks, gets out, floats off, and we can detect in parts per billion. So it's just not possible to hide it. So a successful, inverted commas, test is characterized by that. So, units. The becquerel. Now, again, have you all done this before? Okay, not all of you, right. Well, this is the introductory course. So the becquerel, BQ, is the SI-derived unit of radioactivity. And 1 becquerel is the activity of a quantity of radioactive material in which 1 nucleus decays per second. So if this amount of this water has the activity of 1 becquerel, it means 1 atom in that water is decaying a second. So it's a mass-dependent term. If I had twice the mass of this water in a cup, and what would be the activity? No, twice the amount of water, 2 becquerels. If I had 10 times, it would be 10 becquerels. Just out of interest, how many becquerels do you think that water probably is giving rise to at the moment? No, probably about 1. Bloody hell, I hope it's a becquerel. Struth. No, it's probably 1 or something. What's the major atom which is probably doing the decaying in this? Potassium. It'll be potassium. When you have trucks go through the border from France to the UK, and the detectors go off at the border, what are they detecting? What are the two products that give rise to false positives? Okay, cat litter and bananas, because they've got a lot of potassium in them. In fact, 1 gram of potassium contains 0.000117 grams of potassium 40. All the others are not a problem. So that has a half-life of 10 to the 9 years. So you can work out what is the activity in becquerels. Okay, so that's a little problem for you to go away and sort out. But for a given mass in grams of an isotope with atomic mass Ma and decay constant lambda, the radioactivity alpha can be calculated from, very simple, that equation. And N is Avogadro's constant. Although you wouldn't believe the problems people have in converting becquerels per cubic meter to sort of sievert per square meter. Dose units. So that's activity. That's how you measure activity. But that's not the same as dose. A measure of the energy deposited by the radiation in the material is called the absorbed dose. So the absorbed dose is defined as the mean amount of energy dE deposited per unit mass dm. And you know, we're back to that equation yet again. So the unit of absorbed dose is the Gray, and a Gray is a joule per kilogram. So it's the amount of radiation required to deposit 1 joule of energy in 1 kilogram of any kind of matter. So why would you use why would you use Grays? What's the advantage of Grays over becquerels? Ooh, blimey, I'm sorry, I hadn't got a capital B for becquerel. What is the advantage of the Gray? Well, let's go back to all of these. Look, this type of radiation has got an energy of 0.66 MeV, and this one has got 0.2 MeV, and this alpha particle has got 4.47 MeV, and this one has got 4.60 MeV. So they all have different energies, and, well, let's just stick to the energy for a second. They all have different energies. So yes, this may have the academic activity of 1 becquerel, but 1 becquerel of what? You know, you're comparing apples and oranges. So, the great thing about the Gray is that it tells you how much energy is deposited. And if you're going to disrupt bonds of stuff, of atoms, of DNA, or whatever it is, the bonds of being broken, you're interested in the amount of energy that's being deposited, not the activity. And people still use rads. I just put that down there so you've got the numbers, but I don't pay any attention to that. But the problem with absorbed dose as a measure of radiation protection is that the biological effect of absorbed dose is dependent on the type and energy of the incident radiation. So 1 Gray of alpha radiation will cause about 20 times the amount of damage of 1 Gray of X-rays, because the mass of the alpha particle is different, because the charge of the alpha particle is different. It's affecting us in different ways. In one case, it's producing electron-hole pairs. In the other case, it's producing displacement damage. In the neutron case, it's creating an activated product, which is then decaying with other forms of radiation. So it's still not quite right. So to overcome this limitation, we use something called the equivalent dose. So each type of radiation has a weighting factor. The equivalent dose is a sum over all the types of radiation. So X-rays, gammas, electrons all have an effective number of 1. Alpha particles and heavy ions, because they're big and heavy and high charged, have an effect 20 times greater. Neutrons, bless their hearts, have a rather strange distribution. So if they're really high energy, they only have a value of 5 times. If they're really low energy, they have a value of 5 times. But if they're in the middle, they have a value of 20 times. That seems odd, does it not? Why is a very high energy neutron not considered as damaging? because it doesn't interact much. It just hammers its way through at high velocity. And the interaction, it's so fast, by the time it's thinking of interacting with anything, it's moved on. It's these intermediate energies in here where it's going to really cause the big problems. Subtle stuff, actually. It's really simple, but I would say the devil is in the detail. Does that mean anything? So, then we've got another problem. Different tissue types have sensitivities to irradiation, and so you have this further weighting factor, WT, and it counts for the relative radio sensitivity of different tissues. And this is called the tissue weighting factor. So you end up having to multiply these two weighting factors to each other with the actual dose that you're getting. And together, that creates something called the sievert. The sievert is the amount of absorbed dose in joules per kilogram, weighted to take account of the nature of the radiation and the sensitivity of tissues. And it's the dose of a given type of radiation that has the same biological effect on humans as 1 gray of X-rays or gamma rays. And you can see here that the biological effect of a radiation dose, so it varies from person and source of data, but roughly speaking, 0 to a quarter of a sievert, you just can't detect the effect. There's just no point worrying about it at all. 0.25 to 1 sievert, you get a short-term reduction in some types of blood cells, but no long-term effect. And this is sieverts. This is millisieverts or microsieverts. This is just a single assault, by the way. But very quickly, you go up, and greater than 6 sieverts, yes, end of story. Yeah. So these things are difficult. Of course, I haven't done this now, but there we go.
Is there treatments for this sort of thing?
Sorry?
Is there treatment for...
Yep. This is an extremely controversial area. I mean, right all over notes. This is very controversial. Okay, and I want to go and look at, actually there's something I want to check on that numbers actually.
What was the level measured after post-condition?
Well, it depended. I should get my seat and sit down for this. It depends on whereabouts you were relative to Fukushima. People were evacuated from areas around Fukushima if they got an additional 1 millisievert, it was either 1 or 2 millisieverts a year. And as I said to you at the beginning, if you move from London, where you get 2.8 millisieverts a year, to Cornwall, where you get 7.8 millisieverts a year, you've just increased your dose by 5. So, which is either twice, 2.5 or 5 times more than being evacuated around from Fukushima. And people go on holiday every year to Devon and Cornwall. And indeed, I've been going to Devon and Cornwall for most of my life. And I increased my dose as a consequence. I also will get, let me see if I've got the numbers in here. Oh, I don't have the numbers. Oh, that's a real shame. That's something I should have put in. The amount of dose you get from doing a transatlantic flight or a flight to Australia from the UK, which is much more.
That's not in the Scots.
Sorry?
It's not in the Scots.
Yeah, that's right.
Thank you.
So why is it, by the way, you get a dose of radiation when you fly at high altitude? There's a lot of hydrogen in the air, right, in the form of something called water vapor, and it's really good shielding. So the higher you go, the cosmic rays start to zap you a bit. Again, taking a dose meter, as a friend of mine did, on a plane at high altitude, they don't like that. They really don't like it. He was pretty unpopular for that. I mean, I think he was on an American carrier as well, which really wouldn't be a good idea. So it does go clickety click when you do that. It's not going to do you. I mean, it's still tiny amounts, but it's easily comparable. During Fukushima, there were certain embassies that evacuated their people from Tokyo, and they actually got a bigger dose on the flight back to their home countries than they got if they'd have stayed in Fukushima. Not in Fukushima, in Tokyo, sorry. I mean, by a long way. So, this issue of which particular tissues are sensitive is quite interesting as well. Again, this is the sort of thing radiation protection officers think about a lot. And the answer, gentlemen, is not good. Okay? So, in terms of sensitive tissues, you can see we don't do well on this. And it's the sort of things you'd expect are sensitive. They're these sort of fleshy tissues and so on and so forth. And the one that's really good, of course, is skin. Skin is really a very good protection. And it does make you wonder whether or not that is something to do with evolution. Because skin has been protecting us from all sorts of natural assaults to us over the millennia. And it protects us against radiation. And, you know, the world we've been subject to radiation for a very long time. And, you know, skin does a good job. There you go. This is the business about old units. This is just for your information in case you ever come up against these. You won't do, I don't think, in Australia, but the US still uses Röntgens in units. And the inch. What can you do? So, annual radiation dose to the population. So I'm going to test you out again. So, where does most of your radiation dose come from? Did you look at it? Good.
What was it?
The role about the
Oh, the ozone layer. So there's been some interesting stuff in the news about new chemicals which are really zapping the ozone layer, haven't there? I haven't looked at those yet. Certainly, CFCs really did do a number, but I thought it had prepared itself quite a lot.
Australia doesn't have a pretty strong role.
Anyway, it's worth looking at. So the answer basically is radon gas from the ground. And that's also the second biggest cause of lung cancer after smoking. It's radon from the disintegration of thorium in granite. That's where 50% of your dose comes from. You get 11.5% from food and drink. Coffee, Brazil nuts, eggs, bananas, cabbages, and broccoli. Why? They all have high amounts of potassium in them. 10% from cosmic rays, and 14% from gamma rays from grounds and buildings and building materials and stuff like that. And 15% comes from artificial. 14%, if you're UK, comes from medical intervention.
The history here about mobile phone towers, that they are a source of radiation. That it's actually considered in urban planning, it's a big issue here.
Is it?
What's the data behind it?
I mean, I'm not an expert in that, but I haven't looked at the data, and so therefore I shouldn't make a comment until I've actually looked at it properly. But I haven't looked at it properly because friends who should know about these things tell me that it's a total non-issue. So I haven't looked at it, but I shouldn't really comment too much, even though I just did, because I haven't really looked at the data. But I trust these people who say it's a non-issue. Well, it's like mobile phones, you know. Has there been an increase in cancers due to people using mobile phones? I think there's been an increase in accidents because they're on their mobile phones and not looking where they're going. And actually, I made that comment, but actually, trying to deconvolute these sorts of issues and work out really why, it's actually quite difficult. That was a great example I was giving. And then you get 0.3 occupational, 0.2 from the fallout due to American and Russian and French and British nuclear tests in the 1950s and 60s. 0.2% is from that fallout, and less than 0.1% from nuclear discharges. But if you were to ask most people, where did it all come from? I bet you they wouldn't give you those sorts of answers. And of course it varies from place to place and so on and so forth. And I'm sure, and I'm sorry I haven't got the Australian numbers, and it would be great to have them, but I suspect they'd look very similar. So what did we do to protect ourselves? Well, we used something called ALARA, which is as low as reasonably achievable. In fact, depending on where you are, you either use ALARA or ALARP. In the UK we use ALARP, which is low as reasonably practicable. So what does this really actually mean? And this is really the important thing. We start with the premise that we need to work with ionising radiation, and that the benefit of working with the ionising radiation has to be worth the risk. Actually, we could probably turn off the air conditioning, I guess. Sorry, you're getting cold. Oh, so I thought you were getting cold.
Oh, you know.
I'm a Brit, I can, bloody freezing and I'll still be hot. So the benefit is worth the risk. So we assume that any exposure carries some risk. So any exposure carries some risk. We don't know how much sometimes, but we'll go back to that in a minute. But the point here is we balance the risk and the benefit. Without a benefit, there shouldn't be exposure to radiation. In other words, no unnecessary exposure. I mean, this is called common sense. Really, this is just common sense. So there should never be an overexposure. Right? There should never be an overexposure. So we use the concept of ALARA, or a LARP, to reduce both the external and internal radiation levels to as low as reasonably achievable. And what do? Well, actually, there are three things. Very simple. You minimise the time in a radiation field, you maximise the distance from the radiation source, and you use appropriate shielding wherever possible. What does it mean from a practical point of view? Well, time is minimised by basically preparation and planning to enable swift and efficient working. So you might use a mock-up or computer simulation, and you ensure that only those number of workers actually required to do the job enter the area. So what you don't do, for example, is have a situation you go, ooh, that would be interesting, can I come and have a look? Why? Why do you need to come and have a look? Is there a good reason for you to come and have a look? Is it because you're going to do 20 of those and the person who's showing you really knows what they're doing and it will save you time subsequently? Sure, then you come and have a look. If it's just because you kind of feel like you wouldn't mind having a look, you don't do it. Distance. Staying as far away from sources as the job allows, especially during delays. So you're fiddling around with something over here, and then you realise you haven't got the tool, and Joe goes over to get the tool. You don't kind of stand around like this. You simply move to the other side of the room, and you reduce your dose. It's just common sense, isn't it? But the trouble, what's the trouble with common sense? It's not very common. It's true. It's true. Come on, we've all done these things. I mean, it's not like none of us have done something stupid. But the point here is the distance is great because it's inverse square law. You really don't have to move very far away till you really reduce the dose massively. But of course, you do have to know where the sources are, and they have to be identified. There's no point in moving away from this source over here and say, well, I'll go away from the source, and moving over here if this source is bigger. So you really have to know where things are. And then proper use of shielding. This goes back to the comment I made. You've got to wear the right safety equipment, glasses, types of shielding that aren't going to give you Bremsstrahlung radiation as a consequence of them, and all that sort of stuff. And it all kind of comes down to this thing called the linear no threshold model. And now, in any other context, is there anything quite so controversial as the linear no threshold model? So, what does it say? It relates the amount of radiation dose received to the probability to develop a cancer in the human body. So, radiation carcinogenesis. The basis, try saying that up 2 points. The basis for the non-linear threshold model is if a single particle of radiation hits a single DNA molecule in a single cell nucleus, it might cause cancer. That's the premise. So the probability of such a cancer being caused is linearly proportional to the number of cancer-causing events, which is proportional to the number of particles of radiation, which is proportional to the dose. So the risk is linearly proportional to the dose. So if 1 gray gives cancer risk of R, the risk from 0.01 gray is R over 100. So on this basis, no matter how small, there was always a risk. So this graph goes straight down to 0, 0 there. So the real question that people have asked for a long time is there some sort of minimum dose below which you just don't have an increase in cancer risk? So that's the controversy. So a lot of people think that is the point. Now, it's very interesting. Principal human data upon which this model is based for solid tumours is Japanese A-bomb survivors. So the data is here. Oops. Not winning. Blimey, I moved a long way forward, didn't I? Okay, so all the data's up here. We have no data down there. Why? Why do we not have any data down there?
Well, everyone gets some.
Yeah, but some people get that much, some people get that much, some people get this much. It's absolutely impossible to know where you are on the x-axis unless you carry around monitors all the time. And the problem with radiation workers is they are less likely to die of cancer because they are monitored all the time, and if they do get cancer, they get very early treatment. So actually, the life expectancy of a radiation worker is actually higher as a consequence of this. The real problem is how do you determine, what would you need to do to determine this? You have to do experiments, and you can't do experiments because it's just not ethical. So we're kind of stuck with this model. But it is extremely safe. But it's also expensive, which goes back to your question. So this is something that we're going to have to, and of course what's happened with time is this sort of minimum that we must be careful about has moved back and back and back and back. And you get into all sorts of really quite difficult discussions. So for example, radon gas, which you saw, radon gas is responsible, is the second biggest cause of lung cancer and so on and so forth, if you follow these sorts of models through. And you want to make sure that the radon gas is removed from houses. So houses in areas which have got a lot of granite in their basements now have to be ventilated to try and remove the radon gas so it doesn't accumulate and people don't get larger doses in the house. And I suspect Brittany is an area where Brittany's got a lot of granite, right? I'm sure. Do you have houses, do you have ventilation of houses, basements in houses in Brittany?
Yeah.
I think you do. And this is the reason why. Now, so here's an interesting question for you, and I don't make any comment about this other than pointing it out. We spent in the UK, I think it was 20 million in grants ventilating houses in an area of Devon because of this issue. And if you use the linear no threshold model, then the number of people you would have expected to have got lung cancer as a consequence of the radon in those houses was 1. Statistically, 1. So that just cost 20 million for that one person, whoever that person would have been, to have not got lung cancer, which is nasty but treatable. So the question is, where do you draw the line? How much is a person worth? What a horrible question. You know, believe me, if you're that person, you think it's worth 20 million, right? But how much is society willing to pay? These are very difficult questions that people worrying about these sorts of issues have to contend with. Okay, it's 10 to 9. I'm giving up. So tomorrow we're going to do penetration and shielding, and guess what? We're going to be back to, oh no, it's that equation again.